Good morning, everyone. Today we will be presenting our deep learning project, medical X-ray classification, normal versus pneumonia. Our team members are Spandana and Sunaina. Here is the structure of our presentation. We will begin with the problem statement, then cover the dataset, pre-processing steps, model architecture, training setup, results, challenges, and finally our conclusion and future work. Pneumonia is a serious lung infection and early detection is very important for treatment. However, manually analyzing chest x-rays can be slow and sometimes inconsistent. So our goal in this project is to build a deep learning system that automatically classifies chest x-rays as either normal or pneumonia. This helps support doctors and can speed up diagnosis. We used the chest X-ray pneumonia dataset from Kaggle. It contains around 5,863 X-ray images with 1,583 normal and 4,273 pneumonia images. So it is slightly imbalanced. All images are grayscale in JPEG format. We divided the dataset into 80% for training, 10% validation, and 10% testing. Before training the model, we applied several pre-processing steps. All images were resized to 224 by 224 and normalized. We also used data augmentation techniques like rotation, flipping, zooming, and shifting to reduce overfitting. The images were batched and balanced so the model would learn better. We used a pre-trained ResNet 50 model for transfer learning. ResNet 50 works very well for medical imaging because of its deep architecture and skip connections. We froze the initial layers, added global average pooling, a dense ReLU layer, dropout for regularization, and finally a sigmoid output layer for binary classification. In total, the model had about 23 million trainable parameters. For training, we used binary cross entropy as the loss function and the Adam optimizer with a learning rate of 0.0001. We trained the model for around 10 to 20 epochs with a batch size of 32. We also used callbacks like early stopping to prevent overfitting, model checkpoint to save the best wait life, and reduce LR on plateau to automatically adjust learning rates.
Our model performed very well, achieving around 94 to 96% of accuracy. Precision and recall were also high, meaning the model correctly identifies pneumonia cases with fewer false alarms. Validation and test accuracy were stable, showing good generalization. The model successfully learned the differences in lung patterns between normal and pneumonia cases. Transfer learning helped us achieve high accuracy even with a limited dataset. Data augmentation also improved generalization. The main difficulty was class imbalance, especially because mild pneumonia cases are hard to classify. We faced several challenges during this project. There was a class imbalance with fewer normal images compared to pneumonia. Many X-ray images had variations in lighting and contrast. Some images were noisy and the deep model was prone to overfitting. We addressed these using augmentation and regularization. In future, we plan to train the model on larger and more balanced datasets. We also want to experiment with advanced architectures like EfficientNet or vision transformers. Using Grad-CAM will help us visualize which parts of the image the model focuses on. Finally, we aim to deploy this as a web-based tool for real-time classification. To conclude, we successfully built an accurate and reliable deep learning model for classifying medical x-rays. Using ResNet 50 and pre-processing techniques, we achieved around 95% accuracy. This model can support radiologists by providing fast and consistent predictions. With further improvements, it has the potential for practical clinical use. These are the references used for our project, including ImageNet, ChecksNet literature, the Kaggle dataset, and Kira's document. Thank you for listening. We are happy to take any questions.
I will now walk through the main blocks of our code and explain how each part contributes to the overall pipeline. First, in the setup and imports block, we import all the libraries required for this project. We use PyTorch and Torch Vision for building and training the deep learning model. Torch.nn and torch.nn.functional gives us neural network layers and loss functions. Data loader from torch.utils.data helps us load data in mini batches. From Torch Vision, we import datasets, transforms, and models for image loading, pre-processing, and access to pre-trained models. We also import NumPy, Matplotlib, and skitlearn tools like classification report, confusion matrix, and Rockox code to compute and visualize metrics. Finally, we set the device to GPU if available, otherwise CPU, so the same code can run efficiently on different hardware. In the data setup block, we define where our dataset lives and how it is structured. We point to the root folder that contains train, val, and test directories, and inside each of those we have two subfolders, normal and pneumonia. This folder structure allows us to use image folder which automatically assigns labels based on the folder names. We also define some core configuration values here, such as the image size, batch size, and the number of epochs. By centralizing this configuration, it's easy to change these values without touching the rest of the code. Next, the transformers and data loaders block defines the pre-processing pipeline. We use transformers.compose to resize all images to a fixed size, convert them to tensors, and normalize them using ImageNet mean and standard deviation. For the training set, we also add data augmentation like random rotations or flips to make the model more robust and reduce overfitting. Using these transformers, we create image folder datasets for train, validation, and test splits. Finally, we wrap up each dataset in a data loader which handles batching, shuffling for training, and efficient loading. These data loaders are what we actually iterate over in the training and evaluation loops. In the utilities block, we define reusable functions for training, evaluation, and plotting. The train one epoch function loops over the training data loader, moves data to the device, runs a forward pass, computes the loss, backpropagates gradients, and updates model weights with the optimizer. The evaluate function runs in eval mode and torch.noGrad function, so it doesn't compute gradients. It calculates metrics like loss, accuracy, and saves predictions and labels for later analysis. We also include helper functions to plot loss curves, accuracy curves, and sometimes the ROC curve. Keeping these utilities separate makes the main training code much cleaner and easier to understand. The next block defines the ResNet 50 transfer learning model. We start by loading a ResNet 50 model pre-trained on ImageNet. This gives us a powerful feature extractor that already understands generic visual patterns. We then replace the final fully connected layer with a new linear layer that outputs two logits, one for normal and one for pneumonia. At first, we usually freeze the backbone layers, so only the new classification head is trainable. This lets the model adapt to our medical dataset without destroying the useful pre-trained weights.
In the next block, we implement the training strategy, train the head first, then fine-tune. We start by training only the new classification head for the few epochs with the backbone frozen. This quickly aligns the output layer with our dataset. After that, we unfreeze some deeper layers of ResNet 50 and continue training with a lower learning rate. This is the fine-tuning phase where the model slightly adjusts its feature to better capture patterns in the chest X-rays. We also use early stopping if validation performs doesn't improve for several epochs. We stop training to avoid overfitting. And we save a model checkpoint whenever we get the best validation accuracy so we can later reload the best version instead of the last one. Once training is complete, the test evaluation and matrix block evaluates the best model on the held out test set. We load the checkpoint weights and run the evaluate function on the test data loaders. From the stored predictions and labels, we compute a confusion matrix and the classification report with precision recall and F1 score and the ROC AUC score. These metrics help us understand not only overall accuracy but also how well the model detects pneumonia versus normal cases and where it tends to make mistakes. In the Grad-CAM explainability block, we generate visualization explanations for models' decision. Grad-CAM works by using the gradients of the target class with respect to the final convolutional feature maps. We combine these gradients with the feature maps to create a heat map that highlights the important regions in the X-ray. Then we overlay this heat map on the original image. This is especially important in medical AI because it allows us to show that the model is actually focusing on the lung region rather than the random artifacts, which increases trust and interpretability. The learning rate finder block performs a range test to choose a good learning rate. We start training with a very small learning rate and gradually increase it over a fixed number of iterations, recording the loss at each step. We then plot loss versus learning rate. From this curve, we can visually identify the region where the loss starts decreasing and where it becomes unstable. Based on that, we pick a learning rate in the stable decreasing region. This is simple test help us to avoid guess and check and can significantly speed up convergence. Finally, the mini parameter sweep block runs a small grid search over a few configurations such as different learning rates, weight decay values, and augmentation strength. For each combination, we train a lighter or shorter model and record the validation accuracy. We store the results in a table or data frame and sort by performance. This gives us quick insight into which parameters work best for our dataset without doing a very expensive full scale search. Overall, these 10 blocks together form a complete and well structured deep learning pipeline from the data setup and pre processing through transfer learning and fine tuning, and all the way to evaluation, explainability, and basic hypermeter tuning. Thank you.